Hi again. We're going to continue uh, our discussion of the vibration. Okay, the last thing of structures. So the last thing we discussed is the um, uh, um, damped free vibration. So we said when you have a damped free vibration, under damped free vibration, we said there are three possibilities: under damped, critically damped, or over damped free vibration. And most structures they are in with it, they are under damped structures. For under damped free vibration, the structure will oscillate with a decaying oscillation like this. Okay, what we want to discuss now is how much is the decay from one cycle to another. So here you have a complete cycle from here all the way to here. This is a complete cycle. Or you can measure the cycle from the peaks. So from here you go like this, that's a complete cycle, and then you go like this, that's another cycle, and so on. Measuring the cycle from the peak over here, so this is the first peak, and then the second peak, and then the third, and so on. Okay, let's say this is the peak number I, okay, that happens at the time tau, okay, any time tau that happens here for the peak of cycle I, okay. The next peak will happen, this will be ui plus 1, the peak of the cycle I plus 1. The time in between those, if this is tau plus the period of that takes the structure to do a complete cycle. And we said that the period here for a damped motion is td, which is 2 pi divided by omega d. So td here is the period, which is equal to 2 pi divided by the frequency of the oscillation, omega d. Okay, this is the time in between. So if this is tau, this time from the beginning here is tau plus td. Okay, this is ui and ui plus 1. So if this is ui plus 1 will be less. But what's the ratio? Okay, how much is of the oscillation is lost in one cycle? What's the decay of motion in one cycle? So the decay here is ui divided by ui plus 1. Okay, so this is how we measure the decay, okay, as percentage, okay, or ratio, ui plus 1. Okay, does this decay change from one cycle to another? What do I mean by this? From the first to the second cycle, is the percentage of decay will be the same as you move from the second to the third cycle, from the third to the fourth cycle, from ui to ui plus 1, from the hundredths to the 101 cycle. This is what we're going to see. So the decay ui divided by ui plus 1, ui happens at time tau, okay, so u of tau, ui plus 1 is going to happen at the time tau plus the period td. Okay, so what's u of tau? We found the equation of motion, right? We wrote the equation of motion for an underdamped vibration. Okay, so the equation of motion is like this: just put t equal tau, the time tau. Okay, so e power negative z omega n tau, u naught cosine omega d tau plus u naught u dot naught plus zeta omega n u naught divided by omega d sine omega d tau. Just put t tau instead of t. What about if I want to find the ui plus 1, the amplitude of the displacement, okay, at time tau plus td? Just remove t. Every time you have the time t here in the equation, remove it and put tau plus td. So that's what we're doing over here. Okay, moving down over here. Okay, I want to find u of tau at time tau and u at time tau plus td. So u at time tau, just put tau instead of the time over here, and then u tau plus td. Just here, instead of tau, I'm putting t plus td. E power a plus b is e power a multiplied by e power b. So this is tau plus td. It's going to be the multiplication of the two terms. And then here, a cosine omega d, tau plus td. Okay, as you know, this is a cyclic motion, okay, with that period. Okay, so since here you move the period td, cosine omega d tau plus td is the same as cosine omega d tau. Okay, it's a cyclic function with that period, so it's repeating itself. So this is going to be cosine omega d tau, and this one here will be sine omega d tau. Okay, you just move the period, and this you're going to reach the same exact value. So now the decay, dividing those two terms together, this part within the bracket will cancel with this part in this bracket, and this e power negative zeta omega and tau will cancel with e power negative zeta omega and tau. All you're going to have here is 1 divided by e power negative zeta omega and td. Moving this up, so e power zeta omega and td. Okay, so that's the decay in one cycle. Now, td, the period, okay, the damp period, is 2 pi divided by omega d. So I'm just going to remove td and put 2 pi divided by omega d. So the decay is e power zeta omega n 2 pi divided by omega d. And omega d is omega n multiplied by square root 1 minus zeta squared. So now I can cancel omega n with omega n. So the decay is e power 2 pi zeta divided by square root 1 minus zeta squared. So taking the len of both sides, so len the decay, len e power something is that something directly. So len the decay is len delta over here, and delta is 2 pi divided by square root 1 minus zeta squared. Okay, so and then the decay is e power delta here. This is the decay in one cycle. Okay, the decay here is measured as the peak of the largest, the larger peak divided by the smaller peak that comes after a period after it in time. Okay, so now if zeta is too small, okay, let's say 2% or 1%, so 1 minus 0.02, it's going to be 0.0004. So this is going to be too small, so I can just simply assume that square root 1 minus zeta squared is nearly 1. Okay, so we can take zeta as 2 pi zeta, ignoring this one is going to be 1. So how much is the limitation where you can ignore this 1 minus zeta squared? As you see here, as long as you're, this is 2 pi zeta with ignoring the square root 1 minus zeta squared, and then here this is 2 pi zeta divided by square root 1 minus zeta squared. As zeta increases, the error will increase, but up to zeta of 0.2, okay, the error is so small, so you can actually ignore this part if you want, as long as zeta is below 0.2%. Okay, sorry, 0.2. So delta can be taken as an approximation as 2 pi zeta. If you want to use the exact value, it's 2 pi zeta divided by square root 1 minus zeta squared, and the decay is e power lambda, which is this part, or 2 pi zeta, whatever you want to do. Ignore the square root 1 minus zeta squared or take it into account. So now in one cycle you have a decay of e power lambda. Okay, what about if you have j cycles? Okay, how much the decay will be? In one cycle, e power lambda. The second cycle, e power lambda again. So e power lambda multiplied by e power lambda, so e power 2 lambda. In j cycles, it's going to be e power lambda j. Okay, so that's the decay in j cycles. Okay, so this is, a very nice formula that we get. That's the decay in j cycles. Okay, now let's apply this. Okay, on two examples. Okay, so the first example that we have over here, we're required to determine in the natural period. What's the natural period? Tn. Okay, and damping ratio zeta. Okay, of a frame if the motion under free vibration is given as follows. Free vibration, it means there is no force, it's oscillating. Okay, and it's definitely there is damping. Okay, so there is an oscillation that is decaying. So we have a structure, it's left to oscillate. Okay, we measured the amplitude, okay, of the displacement at the first peak. So it's oscillating. The first peak, the displacement in centimeters was 0.915, and that took place at a time of 1.11 seconds from the start of the vibration. And then the 11th peak, okay, took place at a time of 3.844, and when it was measured, it was 0.076 centimeters. So let's understand what's going over here. We have a frame, okay, and it's oscillating. Okay, how it's oscillating, just understand this. So the first peak here, okay, let's assume it's doing like this. So the first peak, okay, this is the first peak. It took place at a time of 0.11 second, and then the 11th peak, let's say this is 11th peak, okay, it took place at a time of 3.844, and the amplitude of the peak over here is 0.076. Just knowing this information, okay, we will be able to find the natural vibration period, okay, how much is the natural vibration period, and the damping ratio of that structure. How can we do this? Okay, moving from the first to the 11th peak, okay, we have 10 cycles in between. So the time in between is the 11th happened at 3.844, the first happened at 1.11 second. So the difference in time divided by 10 cycles, so one cycle takes 0.273 seconds. The time it takes to do one vibration is the period of the vibration, and this is the damped period. If we assume that, you know, zeta is too small, so the natural period will be approximately equal to the damped period, so the natural period is 0.273 seconds. So that's the first thing that we can find, okay, that we were required to find, okay, the natural vibration period, okay. But here this involves an approximation, okay. We're gonna see if we want to find Tn without that approximation, okay. Now we want also to find how much is zeta, okay, the damping ratio here. So we know the decay, okay, in one cycle ui, okay, divided by ui plus 1 is e power lambda. The decay in j cycles, ui divided by ui plus j, j cycles after this one, okay, is e power lambda j, and lambda is 2 pi zeta with the approximation, or 2 pi zeta divided by square root 1 minus zeta square j. So now, if we take the len of both sides, so len ui divided by ui plus j is equal to 2 pi zeta j, okay? So now, if I want to find zeta, just have it on one side of the equation. So zeta is len ui divided by ui plus j divided by 2 pi j. So what do we know here? We know the amplitude of the deformation or the displacement at the first cycle and the 11th cycle. So u at the first cycle is 0.915 centimeter. At the 11th cycle is 0.076. So len the division here divided by 2 pi j. How many cycles in between? 10 cycles. So doing that division, it's going to be 0.0396. So that's zeta, okay? As you see, zeta is 3%, okay? 3%, so square root 1 minus zeta square, when you say zeta square, 0.0, even 0.04, that's squared, let's get the calculator, 0.04 squared, that's going to be 1.6 times 10 to the power negative 3, okay? 1 minus that value, 0.04 squared, 1 minus the answer, 0.9984. Square root of that, okay, is 0.999, okay? So the error here, if we, is 1 in 1,000. Okay, it's 0.999, okay? So if you actually want to find the exact, okay, Tn, natural period, it's going to be maybe, if this is 0.273, okay, the Tn will be within 1 over thousandths of a difference here. So maybe 0.273, okay, 2. Okay, just a very, very small difference. But anyway, if you want to do it, find it. If you got TD, okay, you can find omega d, which is 2 pi divided by TD. Now you know omega d. Omega d is omega n multiplied by square root 1 minus zeta square. And now you find zeta, which is the 3% or almost 4% over here, this value. You substitute that over here, find the natural period, and then the natural frequency, and then the natural period will be 2 pi divided by omega n if you want to find the exact value. Another example over here, okay, also is a free vibration test. So in this free vibration test, okay, we have an empty elevated water tank, okay. So on that tank there is a cable attached to the tank, okay. and that cable is stretched, so it applies a lateral horizontal force on the top of the elevated water tank. That force is measured, it's 16.4 kips. So you apply a horizontal force at the top of the elevated water tank, a force of 16.4 kips. What will happen to the water tank? It will move with a certain displacement. How much is that displacement caused due to that force, 16.4 kips? It's 2 inches, okay? So that force caused the displacement of 2 inches. And then suddenly we cut that cable, okay? So what do? We remove the force. Now the force applied on the structure is 0, okay? But there is an initial displacement of how much? 2 inches, okay? There is no initial velocity. The initial displacement is 2 inches, okay? Now what will happen to this elevated water tank? It will keep oscillating, okay? As we learned, okay, and the amplitude of the oscillation will keep decreasing, okay, in each cycle, okay. During that oscillation, once we cut the cable, okay, we measured, okay, we kept a record of the amplitude, okay, of the displacement after 4 cycles. So after 4 cycles, the amplitude of the displacement, we started with 2 inches, but it's decaying. After 4 cycles, it became 1 inches. The 4 cycles, it took 2 seconds to finish 4 complete cycles, okay? That's it. So this is an experiment. This is a very nice, okay, experiment, or very nice, you know, testing. If you have an existing structure and you want to you know, assess that structure, know what is the mass of that structure, what's the weight of that structure, what's the stiffness of that structure, what's the natural period of that structure. Already you can get a very, very nice assessment of the structure doing this type of testing. Just apply horizontal force, okay, measure the force that you are applying, see the displacement, let it vibrate freely for a few cycles, measure the displacement after a few cycles and the time that it took to reach, okay, those number of cycles. So from just those 4 data that we have, okay, what are the 4? The force, the initial displacement, the displacement after 4 cycles, the time it took to reach 4 cycles. Those are the 4 pieces of information that we have. From those 4 pieces of information that we have, we will be able to find how much is the damping ratio for that structure, okay, how much is the natural period of the undamped vibration, how much is the stiffness of that structure, the horizontal stiffness for the force, how much is the weight of that structure, how much is the damping coefficient, how much is the number of cycles required for the displacement amplitude to decrease to 0.2 seconds, okay? 0.2 inches, 0.2 inches. So now to solve here the damping ratio, okay, how would we find the damping ratio? The damping ratio is zeta, okay? So simply the decay, okay, e power lambda, lambda is 2 pi zeta j, okay? 2 pi zeta j is ln ui divided by ui plus j. So zeta is ln u node divided by u4, okay? What's u node and u4? This is the information that we have, the amplitude at the first cycle and the amplitude at the end of the 4th cycle, okay? So ln u node divided by u4 divided by 2 pi divided by j, the number of cycles in between those data is 4 cycles. So we have ln, the amplitude of the oscillation at the beginning was 2 inches, and then at the 4th cycle it was 1. So 2 divided by 1 divided by 2 pi and 4 cycles over here. So zeta is 0.0276. Okay, that's so easy to find from that equation. And then TD, the frequency, the damped frequency of vibration for that structure, we had, okay, it took 2 seconds to complete 4 cycles, so it takes 0.5 seconds to complete 1 cycle. That's TD, and we can assume that TD is almost equal to Tn because zeta is too small, so the difference will be square root 1 minus zeta square, and that will almost be, you know, negligible. Now, to find K, the stiffness, we know P equals Ku, okay? You would say, no, P equals Mu double dot plus Cu dot plus Ku. Yes, this is the dynamic equation, but here, before starting the dynamic oscillation, when you apply the force in the cable, P, okay, and there was a displacement that was static application of the force. So P equals Ku over here, okay, before the start of the oscillation. So K is P divided by U. The force that you actually applied on the cable was 16.4 kips divided by the displacement 2 inches. So K is 8.2 kips per inch. That's K, the stiffness here. You need 8.2 kips to give 1 inch, or to move this elevated water tank by 1 inch. Now, if you want to find omega n, the natural frequency of the structure, okay, actually, we already know that it's equal to square root k over m. I know k, I don't know m, but we know Wn. How do we know Wn? Omega n. Omega n comes from here, the natural period. If you know the natural period, you can find the natural frequency. Omega n is 2 pi divided by the natural period. So the frequency is 2 pi divided by the period. So 2 pi divided by the 0.5 second that we have over here, so 12.57, and the period is in seconds, but this one is going to be radians divided by second. So this is important for the units for this angular frequency. Okay, so it's in radians per second because it's an angle divided by time. Okay, so 12.57 radians per second. So now omega n is 12.57. It's equal to square root k over m. K is 8.2 kips per inch divided by the mass of that water tank. So now the mass would be, moving it over here, squaring both sides, is going to be 8.2 divided by 12.57 squared. Okay, what's the units then? It's going to be kips per inch, okay, multiplied by the units of this one. Okay, so kips per inch, and then here you have second squared. Okay, radian is unitless. Okay, so kips second squared per inch. Okay, so that is the mass. Now, what is the weight? The weight is the mass multiplied by the gravity acceleration, or the gravity acceleration is 386. Okay, inches per second square. So inches per second square. So this is going to be in kips, 20. So 387 inches per second squared. So multiplied by this value, it's 20.03 kips. This is the weight, okay, of that structure. It's 20 kips. I know now we evaluated, we knew the weight of the structure just by doing that simple test. Okay, we couldn't, just remove the building and put it on a scale. Okay, but now instead of doing that, you were able to find the weight. Okay, without doing that, unrealistic thing to weight the structure. Okay, now the zeta. Okay, if we already found zeta, we want to find the damping coefficient, C. Okay, we at the beginning, when we introduced zeta, we said zeta is C divided by 2m omega n. Everything here is known except C. We already calculated zeta, the mass of the structure, the natural frequency of the structure. So C is 2m omega n multiplied by zeta. You just put the numbers that you got. So zeta is going to be 0.036, and in the units, you just put the units, all the units, and simplify it. Is going to be kips second per inch. So that's C, the damping coefficient. Now the last thing is, we were asked how many cycles it will take that structure to have it, and for the displacement. We started by 2 inches. How many cycles will it take it? Will it take that structure to have an amplitude of vibration of 0.2 inches? So simply the decay is divided by uj. It's equal to e power 2 pi zeta j. J is the number of cycles in between those two readings. So 2, the initial is 2. At some cycles, because it's going to be 0.2. Which cycle? At cycle j. Okay. So now taking len, okay, of both ends, of both sides over here. So len 2 divided by 0.2 is 2 pi zeta, which was evaluated earlier, multiplied by j. So from here we can find the number of cycles to reach that amplitude 0.2. It's 13.28 cycles. So about 14 cycles. It will take 14 cycles for the motion to get decayed from 2 inches to 0.2 inches, about 14 cycles. Okay, so that was a very nice example. Now, all we discussed until this point, we solved this equation of motion, okay, mu double dot plus cu dot plus ku, and we put the force here equals 0. We had free vibration, okay. If we remove this term cu dot, this is undamped free vibration. When we put cu dot, we have a damped vibration where the vibration decay uh, in each cycle. Okay. Now, what if we have a force here? This now would be called, so this without a force is free vibration. Now with this, when we have a force actually applied on the structure, this would be a forced vibration. Okay. So can we solve this? Okay. Yes, we can solve it depending on how P of T, the force, how the force is changing with the time. Okay. So the most important thing here for earthquake engineering, okay, P of T will be a result of an earthquake. So what's an earthquake? The earthquake, you have a structure that is sitting on the ground, but the ground itself is moving. Okay, the if the ground is moving so slowly, okay, there won't be any force on the structure. Okay, exactly like the example that we mentioned earlier. You have the car and you have the cup. Okay, the cup of coffee in the car. If the car moves so slowly, okay, or accelerates so slowly, even if you're going 80 miles an hour, okay, it's not about the speed, okay, by which the car is moving. If you're going 80 and with a steady velocity, okay, or steady speed of 80 miles an hour, and you're having this cup of coffee on your dashboard, okay, it's not gonna fall down, okay, because you're moving with an 80 miles an hour steady speed. But this definitely, this cup of coffee will fall down, okay, it will get spilled on you when you apply a sudden brake or sudden acceleration, okay, it will start moving at that time, okay. So it's the same here. You have the structure and then the ground is moving, okay. So when you have this sudden movement of the ground, okay, how do we mean, or what do we mean by sudden? Okay, you have a large acceleration. So the what we measure here is the acceleration of the ground. So ug is the ground acceleration. G stands for the ground, and double dot means the acceleration. So the ground acceleration over here in terms of time, you have an earthquake that gives a rapidly changing ground acceleration like this, okay. So now if you have this ground acceleration, this will give a force on the structure. The force will be negative, okay, exactly like the example of the coffee, okay. The car moves forward, the cup moves backward, okay. The cup of coffee moves backward, okay. So the ground is moving forward, the structure will be, there will be a force that is applied backward on the structure. So the force applied on the structure will be negative m, the mass of the structure, multiplied by ug double dot, okay, the ground acceleration. So actually, this is the force that comes from an earthquake, the ground acceleration multiplied by m, the mass of the structure. So the larger the mass of the structure is, the larger the force that is going to be applied on, okay. So ug double dot is the ground acceleration here. So actually, when we have an earthquake, if we measure the ground acceleration, we can know, okay, the force that is applied on the structure. It will look exactly like the ground acceleration like this, okay. Now, how can we solve if the equation of motion if we have P of t, okay? If P of t is a simple analytical function, for example, like a harmonic function like this, or step function, or a ramp, okay, like this, okay, those are simple forces, so simple forces, okay? You can find an analytical solution to that equation over here, okay? If P of t is simple, just a harmonic or a constant function or a ramp function, okay, we can solve this by hand. Analytical is that you can find a closed form mathematical solution for this. But if it's a, you know, an arbitrary force that comes from an earthquake, okay, you can't actually define the force, okay. It's so hard to define the force, so we won't be able to find a mathematical solution for that. Instead of finding an analytical solution, we're going to actually find a numerical solution. So we need to define a numerical method that we will be able to find the displacement when you have a force that will look like an earthquake force like this, okay. Changing, you know, without any, you can define the force over here. It's so hard to give a function closed form for the force applied from that have this shape, okay. So what numerical methods? There are many numerical methods there is something called the Duhamel's integral. It's an integral force that can be used, to have a numerical solution of the equation. Time stepping methods. There is a method called Newmark's beta method, Wilson theta method. Okay, so since our course we're not having the entire semester, it's just half of the semester, we're only going to cover few of those methods. We're going to cover the Duhamel's integral and the time stepping method. This is to solve numerically for the the displacement. Okay, due to an arbitrary force. Okay. So before doing so and understanding those numerical methods, okay, we're going to first try to find an analytical solution for certain simple forces applied in structure. So let's start if P of t is constant, P naught, okay? P, so the force applied in structure is constant, P naught. You would say, okay, that's a static force. No, okay? This force is applied suddenly on the structure, okay? So at time 0, okay, or just a little bit before time 0, there were no forces, and then suddenly when you had a force at time 0, you apply the force suddenly, that is equal to P node, and then you keep it on the structure, okay? So how will the structure perform under the application of a sudden constant force, okay? So the equation of motion, let's put here P of t equal P node, it's a constant, so P is not function of t, okay? So mu double dot plus cu dot plus ku is equal to P node, okay? Now to solve this, according to what you learned in the differential equation course, okay? If you remember that, or you need to revise this part in the differential equation course that all of you took, okay? To solve this equation, okay? The solution for this equation, u, we're looking actually for the function u. How much is u, or what's the function u that satisfies this equation? U as function of t. There will be, it's going to be a summation of two functions. One is called the homogeneous solution, and then the particular solution. The homogeneous solution is the solution that satisfies this equation when this term is 0, which we already done before. Okay, so homogeneous solution here is when this, here we assume that this is 0, because here you have B node plus 0. So this equation should satisfy both terms when there is P node and 0. So when there is 0, it's the homogeneous solution, and we solved this before. It's e power negative zeta omega n t, a cosine omega dt, and b sine omega dt, and we find those constants. A is u node, and b is u node plus u node double u node dot divided by omega d. I don't remember that exactly. Let's go up there. Okay, we found that earlier. So over here, okay, the two factors a and b. Yep. Yeah. So a is u node, b is u dot node plus zeta omega n u node divided by omega d. Okay, so that's the homogeneous solution. Okay, so let's go over here. So now that's the homogeneous solution. We already did that. Okay, now for the particular solution of this, there is a method called the method of undetermined coefficient. What does the method of undetermined coefficient say? It's a mathematical method that you should have learned in the differential equation class. Okay. So you assume that the solution, the particular solution, okay, is a function, an analytical function, an algebraic function, okay, that has terms, okay, that is equal to the higher or the highest power of the term over here. This term in power of t, it's just b node, it's a constant. So we're going to assume that the particular solution is a constant d, okay? So now, if the particular u is a constant d, the velocity or the differentiation, if you differentiate this with respect to time, it's going to be 0. So u p dot is 0, u double dot p of the particular solution is 0. Let's substitute those three values in the equation here. Mu double dot, that's 0, cu dot is 0, ku, k multiplied by constant d, is equal to p node. So k multiplied by d is p node. So simply this constant is p node divided by k. Now we find the two solutions, the homogeneous and the particular solution. Okay, the homogeneous solution is e power negative zeta omega n t. a cosine omega dt plus b sine omega dt plus the particular solution p naught divided by k. Okay, so now, okay, how much is a and b? Okay, are those the values that we got? No. When you apply the initial or the boundary conditions, you should not apply the initial or boundary conditions on each solution separately. You should apply the boundary conditions, okay, on the entire solution that you have over here, the homogeneous plus the particular solution altogether, okay, because that's the total displacement, okay, that we have. So now, okay, assuming that we start with a zero initial displacement, okay, so u node is 0. When the time is 0, u node is 0, and u dot node is 0. So let's put here u node is 0. So we're going to have, this is when the time here is 0, e power 0 is 1, multiplied by a cosine 0 is 1, and b sine 0, 0 is 0 here. Sine 0 is 0. So plus b node divided by k. So from that we can find a, it's going to be negative b node divided by k. To find the other constant b over here, we need to use the other boundary condition. The velocity at the beginning of the motion is 0. Okay. So from this here, we need to find the derivative to find the velocity. So the derivative, you have to find. It's going to be e power negative zeta omega nt multiplied by the derivative of this bracket plus this bracket multiplied by the derivative of e power negative zeta omega nt. So this is the first bracket, and then the derivative of the bracket, and then this is the derivative of e power negative zeta omega nt. It's going to be negative zeta omega nt multiplied by e power negative zeta omega nt multiplied by what we had in the bracket over here, plus the derivative of b node divided by k. P node divided by k is constant, so the derivative is 0. Okay, now the initial velocity u dot node is equal to 0, okay, when the time is 0. Just put time 0 here, so e power 0 becomes 1, and then sine here becomes sine 0 is 0, and then cosine 0 is 1, so b omega d multiplied by 1 minus zeta omega n, e power 0 is 1, and then a cosine 0 is 1 plus 0. We already found a was negative b node divided by k, so from this we can find b. So the constant b would be negative b node divided by k multiplied by zeta divided by square root 1 minus zeta square, and a is negative b node divided by k. Let's substitute those two in the equation. So u is e power negative zeta omega nt multiplied by b by a, which is negative b node divided by k cosine omega dt, plus b cosine omega dt, that's b here, which is negative b node divided by k multiplied by zeta divided by square root zeta 1 minus zeta squared, and then plus b node divided by k. As you see here, we have b node divided by k in each term over here, so I can take this as a common factor, b node divided by k multiplied by 1, so 1 minus e power negative zeta omega nt cosine omega dt, and then over here we took this as a common factor for those two terms here, so we have cosine omega dt, and then here we have the negative, so this becomes positive zeta divided by square root 1 minus zeta squared sine omega dt. So this is the solution over here. So as you see, the solution is b node divided by k multiplied by some factor. What's b node divided by k? If you apply a force p node, the displacement, okay, if you apply static force of b node, not a dynamic force, static force of b node, okay, the displacement will be b node divided by k, okay? So that's the static solution, okay? If there is no dynamic response, there is no oscillation, okay? This is what you would expect. P equals ku, so u is p node divided by k, okay? That constant force. But actually there is a vibration, so it's going to vibrate about this value 1, so this is multiplied, this is the displacement that we have, and we are always subtracting this oscillation from it. E power negative zeta omega nt cosine omega dt plus zeta divided by square root 1 minus zeta squared sine omega dt. That's an oscillation. Cosine and sine omega dt is an oscillation. And what's this term in front of the oscillation? E power negative zeta omega nt. We discussed this before, okay? That's a decay. So you're having a static displacement that you could expect, and there is an oscillation or a decaying oscillation subtracted from it, okay? So what does this mean? If we plot it, okay, so this is u of t as function of t. So this is the displacement over here as function of the time. If the force was applied in a static manner, this is the displacement that you would get, okay? But now it's oscillating. You're having an oscillating value. It's going to start from 0, okay? You apply the force suddenly, so the displacement is 0. You're going to go up, okay, and overshoot, okay? When will you overshoot? When this term becomes negative, so negative multiplied by negative, you can have a higher value, okay? 1 and then plus something. So P naught divided by K plus some oscillation over here. So you're going to overshoot, okay? And then you're going to go down, and then negative when this becomes positive. So 1 minus this oscillation over here. You're going to go below U static, and then you're oscillating about this static force, okay? And then this oscillation is decaying, okay? At the end, and when you reach the steady state, when at the time of infinity, okay, this oscillation will go to 0, okay? So you're oscillating about U static over here. At the end of time you're gonna reach this static force because the force is still applied, okay? So actually, now when you apply the force, okay, suddenly, okay, you didn't get U static like this, okay? No, you vibrated around this U static. This is the dotted blue curve that we have over here. Why you have this decaying oscillation? Because you have zeta, you have a damped motion. What if you didn't have zeta? There is no damping. Zeta is 0. This becomes 1. This omega d will be omega n. Zeta here, if it's 0, this term is going to cancel, okay? Zeta divided by square root 1 minus zeta squared, okay? So you're going to have an oscillation, okay? But this oscillation will not be, decaying. It will oscillate forever. And we said definitely this is not realistic because there is no case where there is no damping. There is always damping, okay? There is always frictional damping. So those are the two solutions. The red one is the undamped. The blue one is the damped oscillation, okay? When you have a constant force. So here, this is the solution when we had a constant force applied, okay? But what was the initial conditions? There was no initial velocity, there was no initial displacement, okay? What if there was an initial velocity or initial displacement? Simply, I would add the terms that comes from initial velocity and initial displacement for the unforced, okay, or the free vibration, okay? Now, let's take this one step, harder. Instead of having a constant force, okay, no, we have a linearly increasing force, okay? So P of t is starting from 0 and it's increasing linearly like this, okay? So how do I write P of t? It's a linear function. Let's say after some time tr, okay, you reach an amplitude of p naught, okay? So how much is the slope then? The slope is this p naught divided by tr, and then this is the slope you multiply by t. So the function here is it's a function of the time. So it's the slope multiplied by t. So P of t is P naught divided by tr, constant, multiplied by the time. As the time increases, the force is increasing to infinity, okay? So it's a linear function. B is a function of t, not t squared or anything. So the slope multiplied by t, okay? And there is no constant over here because you start from 0, okay? The force starts from 0. So now this is, if the force is like this, what is the displacement? How will the displacement look like? Just put B over here, so mu double dot, the equation of motion is mu double dot plus cu dot plus ku is equal to the force. Now this is the force. It's a function of the time, t divided by tr p naught. As we said, there will be two components, the homogeneous component or complementary solution, okay? So e bar negative zeta omega n t multiplied by a cosine omega dt plus b sine omega dt. The particular solution, how do we find the particular solution? We assume it's a function, okay, you know, a summation of algebraic functions that have the highest term that is equal to this one here. So this is t, so we're going to assume it's dt plus some constant. This is just an assumption. How much is d, how much is f? Can d be 0, can f be 0? We're going to see, okay? So this is the particular solution, it's dt plus f. So the differentiation, the derivative of this will be the velocity, okay? U dot b is d, and then the double dot, the acceleration would be 0. The second derivative will be 0. D becomes 0. Okay. So now let's put those three functions here in the equation over here. Mu double dot u is 0, so we cancel this term. Cu dot c u dot is d, so c multiplied by d. Okay. Plus ku k u is dt plus f. So k multiplied by dt, so dkt plus k multiplied by f. So kf equal to the force over here, t divided by t r p naught. So we have this equation, okay? This equation, on the right hand side of the equation over here, you have a term that has time, okay? And here you have a term that has time, okay? So for this equation to be satisfied, this term has to be equal to this term. So equating the coefficient over here, you have dk multiplied by t equal t divided by, sorry, p naught divided by tr multiplied by t as well. So p naught divided by tr has to be equal to dk. So dk has to be equal to p naught divided by tr. From that we can find that constant that we assumed over here, d. So d is p naught divided by ktr, okay? On the other hand, we have cd here plus fk has to be equal to, this is a constant term. What's the constant term on the right hand side of the equation? 0. So cd plus kf has to be equal 0. cd plus kf has to be equal 0. So f has to be equal to, we're looking for that second constant, f over here, okay? So f is negative c divided by kd. C is the damping coefficient, k is the stiffness, d, we already found d from here. So negative c divided by k multiplied by p naught divided by ktr. So we're going to have k squared over here. Negative c p naught divided by k squared tr. Okay, so the particular solution now is dt plus f. Now we found d, so it's p naught divided by ktr multiplied by t. Those are constants, okay? P naught divided by tr is the constant slope of the force, k is the stiffness of the structure, and then f here, it's negative cp naught, okay? C is the damping coefficient, p naught is the slope, p naught divided by tr is the slope, and k squared is the stiffness squared. Okay, so now the solution is the particular solution plus the complementary or homogeneous solution. So the homogeneous solution is e power negative zeta omega nt a cosine omega dt plus b sine omega dt plus the particular solution, those two terms that we had over here. Now still we have to find the two constants here, a and b, okay, from the boundary conditions. Doing so, okay, just do the same, okay? Let's assume an initial boundary condition of 0, no initial displacement, no initial velocity, okay? You just have the force, okay? So u node equal to 0 at time equals 0. Just put the time equals 0 here. This becomes 1, this becomes 1, so a plus 0, time here 0, so this term cancels, and you're going to have this term. So a minus cp node divided by k squared tr. From that, a has to be equal to cp node divided by k squared tr. Okay, let's simplify this one a little bit. We know that c is equal to 2m omega n zeta, okay, and k squared is equal to m omega n squared. Omega n squared root k over m, so k is m omega n squared, okay? K squared, okay, is, yeah, so just substituting those values over here, okay? We're gonna get that a is 2 zeta divided by omega n tr, okay, multiplied by p naught divided by k, okay? So that's the constant a, okay? Now, okay, finding the velocity of the vibration, okay, the velocity will be the derivative of this one. So it's going to be e power negative zeta omega nt multiplied by the derivative of this bracket, and then this bracket multiplied by the derivative of e power negative zeta omega nt plus the derivative of this part, which is p naught divided by ktr, plus the derivative of this part. This is constant, so it's going to be 0. So this is the derivative over here that we mentioned, okay? And then you put at time, just every time you find time, put it 0. The time is 0, so this term becomes 1, this one becomes 0, 1, 1, 1, 0, and then equate this, put the display, the initial velocity equal to 0. So from this, okay, so 0 and so on, I solve for b, okay? So simply, if you do this, you know, simplifications, you're going to find that b will be p naught divided by trk multiplied by 2 zeta square minus 1 divided by omega d. So let's simplify it a little bit more, okay? And put everything here in the equation. So u is going to be p naught divided by k, t divided by tr minus 2 zeta divided by omega n tr plus e power negative zeta omega n t. So we have an oscillation term over here. So we have a linearly increasing displacement. We have a constant displacement, okay? So we have a linear part, okay? And a constant part, an oscillating part, okay? So this is the displacement, okay? As function of time, if you have a linearly increasing force, okay? We also find the displacement if we have a constant force, and we found the displacement if we have an initial displacement, okay? So this is when you have an initial or a constant force here. This is when you have a constant force, and if you have an initial displacement, it's simply going to be e power negative zeta omega n t, okay, multiplied by the initial displacement multiplied by cosine omega dt. If you have an initial displacement, the initial velocity, it's just going to be e power negative zeta omega n t multiplied by b multiplied by sine omega d t, and we can find b from the initial velocity as we did earlier, okay? Now, those are solutions, okay, for certain functions. A constant function, a linearly increasing function, okay? Usually an earthquake, okay, will not be linear, will not be constant, okay? Usually an earthquake will be a random force, okay? So if b of t is a random force, how will we solve for the displacement, okay? We have to use a numerical method, okay? So we're going to have two numerical methods that we're going to be discussing over here, okay? So what are those two numerical methods? The first one is called the time stepping method. The time stepping methods, okay, depends on those solutions that we found, okay, for a linear force and for a constant force, okay, and for an initial condition of initial velocity and initial displacement, okay. So let's see how the time stepping, okay, method works, okay. We're going to derive it over here. And then all you need to do is just use the final, okay, formulas that we're going to find over here to use the time stepping in a numerical method, okay? So now let's assume you have the force applied on the structure. It's changing in time. P of t is changing with time. Some random force like this, okay? This force is sampled at every delta t, okay? So you have the amplitude. You sample this at amplitudes, okay? You sample the amplitudes every certain step, delta t, okay? So the smaller the delta t, the more accurate you're defining the force, okay? So you're defining the amplitude here every step, delta t, okay? The smaller delta t, the more accurate it is. This is so important, okay? So for example, if you sample this at maybe 1 second, you're losing a lot of information. So maybe here, if you sample it here, you assume that there is a linear force in between, okay, which is not the case. You have different, okay, values over here, so you need this sampling step, okay, delta t, okay, the step to be as small as possible, and then you define the force as the amplitude at those sampling points, okay. So you have P1, so P node, P1, P2, P3, P4, and so on, and when here you have some step, okay, so this is the first step. Second step, you have Pi over here, the 10th step, okay, Pi at the end, and then the next one is Pi plus 1, okay. and this continues until the force ends. Okay, you sample it until the end of the force. Now when you apply this force, there will be a displacement. Okay, we want to find this displacement. We want to be able to find a closed form solution as we did with the force. Okay, instead of this, okay, we're going to be finding the displacement. Okay, at those sampling points. Every delta t, we're going to be our target is to find this u at those sampling points. So u1, u2, u3, u4, and so on. ui plus 1 at those sampling points at the start of this sampling point, the end of this step. Okay, and so on. Also, we're going to be finding u dot of t. Okay, at each of those sampling points. Okay, so how we're going to be finding those? Let's study this sampling step at step pi. Okay, at step I over here. So you had maybe 10 or 1,000 steps before reaching this one. I can be 1,000, 100. Okay, you had 1,000 steps before. Let's start with this step pi. Okay, let's study just this step. The start pi, the end is pi plus 1. This is the force that you have. So in this step, okay, this is the step that we have here, p of t. Okay, this starts at some time t, p of I, at some time t, depending on how much is I. Okay, 1,000 steps before that, 100 steps. So at some time t, the force is pi. Okay, and then at the end, okay, you have, if this is t, sometime t. Okay, at the end of this step, the time will be t plus delta t. Delta t is the sampling time. Okay, at the end is going to be pi plus 1. Even if the force is not linearly changing, we're going to assume, since delta t is small, we're going to assume that the force is changing linearly. Okay, so you start with pi, and then the force changes linearly between pi and pi plus 1. Okay, so now if we assume that the force is changing linearly, so in this time, in this delta t, okay, the force is a constant force plus a linear force that starts from 0. Now you can relate why did we find, okay, a closed form solution for a constant force, okay, and a linearly increasing force, because we're going to use that over here. So now at pi, at the start of the step, okay, we know the force that goes all the way from this time to the end over here. Okay, what about the displacement? How will the displacement change within that time? Okay, here you have ui and ui plus 1. If you know ui at the beginning over here, okay, how will I know ui? That's what we're going to mention. Okay, so ui, if you know ui, we're going to be able to find ui plus 1. Okay, so if you know the starting amplitude of the displacement over here, okay, ui, okay, you're just going to assume that there is a free vibration, so ui will be multiplied by e bar negative zeta omega and t multiplied by cosine omega dt. Okay, and if you know the velocity at the beginning as well, okay, you're going to multiply this by its factor. Okay, and then you're going to add this to the effect of the constant force and the effect of a linearly varying force. Okay, so to find the amplitude of the displacement at the end over here, we can find ui plus 1 only if we know how much is ui and how much is ui dot. Okay, so I need to know what's the displacement at the start, the displacement, the velocity at the start of a step, to be able to find the displacement and the velocity at the end of that step. Okay, once I find the velocity and the displacement at the end of the step, I move to the next step, and those displacements ui plus 1 becomes the starting condition for the next step. Okay, so I move step by step. I solve one step, find the displacement, the velocity at the end of the step, and then I use it to start the new step. Okay, so as you see here, ui dot u dot I are known from the previous step, solving the previous step. So here we are approximating the force as a linear force. Okay, so now, okay, how can we find this? Okay, so at any time t, u of t, okay, will be we're going to have 4 parts of solution. Okay, one due to an initial velocity and displacement. This is the part due to the initial velocity and displacement under free vibration. If you just revise the equation due to the free vibration, that's what we have when we have an initial velocity and an initial displacement. So e power negative zeta omega nt multiplied by ui, so this is the term due to an initial velocity, ui cosine omega dt, plus the term due to an initial velocity, ui dot zeta omega and ui divided by omega d sine omega dt. What if I have a constant force? This is the part that you're going to have due to a constant force, but with no initial conditions. The initial conditions comes from here, okay? The initial conditions, if they are 0, it's going to be pi divided by k, 1 minus e power negative zeta omega nt multiplied by cosine omega dt plus zeta divided by square root 1 minus zeta square sine omega dt. Why I'm saying this so fast? This is what we got for the constant force. Just go to the constant force, you're going to find that this is what we have, okay? Why I'm putting pi over here? Because I'm assuming in between this time, okay, from t to t plus delta t, okay, I have a constant force. The constant force will be pi, okay? And how much, what about the damp over here? The difference, the height here is pi minus pi plus 1 minus pi, okay? That's the difference. This is the height over here. So the slope is going to be pi plus 1 minus pi divided by delta t. That's the slope. So now, if you have the ramp force, this is the solution. Pi plus 1 minus pi, that was p node, divided by k, multiplied by t, divided by tr. Now tr is delta t, okay? Minus 2 zeta divided by omega n tr, which is delta t, plus this oscillation, okay? So where did you get, we get this from? From the ramp, the solution that we got for the ramp force, okay? So now, how much would be the displacement at the end of the time step? So if this is u of t, this is at the beginning, okay, this is the equation, okay, measured, okay, from any time from the beginning of that time step. Just putting t equal delta t, we're going to be able to find the displacement, the velocity, okay, at the end of the time step. So this is equal to delta t. We start with u node, u dot node, okay. We want to find those at the time delta t from the start of the of our study. So just putting delta t, t equal delta t in this equation, we're going to be able to find u of delta t. Just put here delta t. Just anytime you find t, just put delta t. Delta t is the time step. It's the sampling time that you have, okay. You're going to put it here, 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 and so on. Okay, here, this is already delta t, t divided by delta t, t is going to be delta t, we're going to put delta t over here, so this becomes 1, t becomes delta t, and so on, okay? So this is what you get, okay? Delta t divided by delta t, this is going to be 1, okay? So as you see, this is ui. If you know ui, you are going to be able, if you know ui and ui dot, okay, the displacement, the velocity at the beginning of the sampling point, you know the force at the beginning of the sampling point, you know the force at the end of the sampling step, okay? You're going to be able to find ui plus 1, the displacement at the end of that sampling point. It's going to be that formula, okay? As you see here, we're going to have some terms, okay, that are multiplied by ui. So for example, this term is multiplied by ui. This term here is multiplied by ui. Here nothing is multiplied by ui, nothing is multiplied by ui. So actually, if we sum the terms that are multiplied by ui, that's going to be a factor a. It's going to be e power negative zeta omega n delta t cosine omega d delta t, and then e power negative zeta omega n delta t multiplied by zeta omega n ui divided by omega d sine omega dt. So that's the factor a. I'm just summing all the factors that are multiplied by ui, okay? That's going to be a over here. And then b is going to be the summation of all of the factors that are multiplied by ui dot. I have ui dot over here, so that's a factor that's going to be b. And then there is some factor multiplied by pi. Pi, there is a factor pi over here. Here it's pi multiplied by all of this, so this is the factor multiplied by pi. Here we also have negative pi divided by k, so all of this multiplied by negative 1 over k is going to be multiplied by pi. So I need, this is going to be c. D is the term multiplied by pi plus 1. So it's going to be, here you have pi plus 1 divided by k, so D is going to be all of this term divided by k. Okay? So those are A, and then also finding the derivative, deriving u, or finding u dot, finding the derivative of the equation over here, this equation. If you derive u of t and then put delta t equals 0, you're going to be able to find u dot at I plus 1, okay, at the end of the time step. Okay, you derive this, you're going to find u dot of t. You put t equal delta t, that will give you the velocity at the end of the time step, which is u dot I plus 1. Okay, so again, u dot I plus 1 will be some, you know, factor a prime multiplied by ui plus some factor b prime multiplied by ui dot plus some factor c prime multiplied by bi plus some factor d prime multiplied by pi plus 1. And you can find those factors exactly the same way we did over here to find a and b and c and d. Okay, so those factors, okay, will be like this. Okay, from the derivation, those will be the factors. Okay, so a, b, c, and d, a prime, b prime, c prime, d prime. Okay, so simply, as a summary, I know that you might be a little bit lost over here. What do we know? Okay, so let's go back to what's the problem statement, the numerical solution, okay, of the method. What do we have given? You're going to be given the force, P of t, and it's given as sampled at delta t. Okay, so you have P node, P1, P2, P3. Okay, so what you're given here is Pi. Okay, the force at some point. Pi from, and I is from 0 to n. Okay, what are we looking for? We're looking for u node, u1, u2, u3, ui. Okay, you're looking for ui at all of those sampling points, and you're looking for ui dot. Okay, the velocity at those sampling points. Simply, how you're going to do this, you're going to move step by step. If you know the initial condition, u of 0, you know u of 0 and u dot of 0, okay, you start with an initial condition. Let's say the initial condition is 0. Structure is standing over there. There is no earthquake yet, so the initial condition is 0. Okay, it's not moving. There is no initial displacement. There is no initial velocity. And at once you start applying this force P of t. Okay, so how will the displacement, you know, build up to u1, u2, u3, and so on? How will the velocity build up? You know the initial condition, and you need to go step by step. Find u1, u1 dot, okay, u2, u dot 2, u3, u dot 3, and so on. How will you jump from one step to another? Simply through those equations that we mentioned. Okay, those ui plus 1, if you know ui, you start by knowing u0, right? You know the initial condition at step 0. You multiply the factor a multiplied by the displacement at time 0, plus b multiplied by the velocity at time 0, plus c multiplied by the force, the sampled force at time 0, plus d multiplied by the sampled force at the end of the first step, pi plus 1. How much about the velocity at the end of the first step? It's a prime multiplied by the initial displacement, plus b prime multiplied by the initial velocity, plus c prime multiplied by the initial force, plus d prime multiplied by the force at the end of the first step. How much are a, b, c, d, a prime, b prime, c prime, d prime? You don't have to memorize those. Those are here. They are in the textbook. Okay. What are those factors? They depend on zeta. So zeta, the damping coefficient. Sorry, damping ratio. Omega n, the natural frequency of the structure. Delta t, the sampling step. Okay. How much is delta t? Omega d. Okay. Those are all the things that you need over here. K is the stiffness. Okay, so once you know the properties of the structure, all of those are properties of the structure itself. Omega n is a function of the structure. Okay, it's not changing. Omega n is square root k divided by m. Okay, zeta depends on the damping coefficient. It's constant. Okay, delta t also is a constant. It's the time step. Okay, maybe 0.001 of a second. Okay. You find, so those all are constants. You just need to find those once. Okay, a is going to be a constant, b is going to be a constant, C is going to be a constant, and so on. So to solve the problem here, you first need to find all those constants. How many constants? 8 constants. A, B, C, D, A prime, B prime, C prime, D prime. Once you find all those 8 constants, you can go step by step. At step 0, the time is 0, the force is P node, okay? And then ui is the initial displacement, the velocity is u dot node. At the end of the first step, okay, so step 1, you move the delta t. P, the force now is P1. How much is U1? It's A, U node, the displacement at the previous step, P, B, U dot node, the velocity at the previous step, C, P node, this one, plus dB1, okay, this one, and then the velocity here comes from this equation. So you have those at the beginning, you have this, those are given, the forces here are given, the sampled forces, okay, and you start filling this table, okay, one by one, okay, row by row. If you want to find U2, U2 is going to be A multiplied by U1 plus B, U dot 1 plus C, B1 plus D, P2, and this one is going to be U2 dot U dot 2, A prime U1 plus B prime U dot 1 plus C prime B1 plus D prime P2. Okay, so you won't be able to find the displacement, the velocity at the second step before finding the displacement at the first step first. To find the displacement at step I plus 1, you need to find the displacement at I. So you go, fill this step by step. I hope you understand this. If you have any problem with this, please let me know. You're going to have an assignment. The first assignment is simply, okay, an application on this. You're going to be writing a code, a MATLAB code, or you maybe would like to use Excel, an Excel sheet. That's fine. Whatever you want to use, okay. You're gonna have an earthquake excitation. There is a very famous earthquake called El Centro earthquake. Okay, so the ground acceleration of this El Centro earthquake, okay, in the north-south direction. The components, the earthquake, the ground excitation of the earthquake is recorded in the north-south direction, in the east-west direction. So you are supposed here to use the earthquake excitation. So what is given for the earthquake excitation is U double dot G, UG double dot, okay? The ground acceleration, okay? So if you know the ground acceleration, okay, how much is the force? Simply, you're gonna multiply this ground acceleration, okay, by negative m UG double dot. Why is this? Because this is the force, as if you remember, okay? This is what we mentioned over here. If you have a ground acceleration, the force is negative m UG double dot. So you're gonna go online, okay? I'm giving you a link that will have the data points, okay? The sampling point for this ground acceleration for that El Centro earthquake, okay? You just multiply this by the mass of the structure, minus m multiplied by U double dot G, okay? And you find the force, okay? Once you find the force, okay, you're gonna put it over here, okay? You have the forces. You're gonna find all those constants based on how much is zeta, how much is omega n, okay? Delta t is the sampling, that you're just gonna see how much is sampling points for the data for the earthquake excitation, okay? The ground excitation, how much is zeta, omega n, omega d, those will be given to you in the assignment, okay? And then you fill up that table. You have B node, you're going to import this from the internet for the El Centro ground acceleration. You start with 0 and 0, and then you go ahead, find the factors A, B, C, D, A prime, B prime, C prime, D prime, okay? And then you just, code, okay? You're going to have this, filled by the computer. You're just going to need to tell this formula to the computer, link this cell with the cell before it. Once you know this and this, you substitute them over here. You know those two cells, you substitute them over here. You know those two cells at step 2, you find the displacement, the velocity at step 3, and so on until you find the displacement and the velocity at the end, okay, of the excitation, okay, of the ground excitation, okay? So that was the first method, okay? Now what about the second method? Okay, so the second method is called Duhamel's integral. It's an integral force, but you can actually use it as a numerical method as well. Okay, so what is the rationale behind the Duhamel's integral? Now, assume we have a structure or a pendulum like that looks like this. Okay, there is a mass over here. Okay, and we have a force applied. Okay, an impulse force. Imagine that there is this pendulum, and you have a a baseball bat, okay, and then you hit that mass, okay. You're applying an impulse, okay. So when you just touch the mass, okay, you're applying an impulse force, okay. The mass, the displacement will be 0. Once the impulse, okay, you apply the force and then there is no contact now, okay, you are giving the mass, okay, an impulse that will suddenly give that mass a velocity, okay, an initial velocity. But the impulse will not give an initial displacement. The displacement is 0, okay. The velocity then will make the object move, okay, with that velocity. So the integration of the velocity will give you the distance, but the initial distance is 0. You start from here, but then you hit it with an impulse force, okay. You give a velocity. How much is that velocity? Okay, depending on the impulse. How much is the impulse? The velocity we can find the velocity. Okay, so depending on the impulse, what's the definition of the impulse? The impulse is P multiplied by T. You apply a force P for some time T here. Okay, delta T. You apply an impulse force like this. P for some time delta T. Okay, that's the definition of an impulse. Force applied for a small period of time. So from Newton's second law, we know that mu double dot is equal to P, okay? If I integrate both sides here, so the integration of mu double dot dt, okay, is equal to P dt, okay? So I'm going to integrate this from T1 to T2, the time where this force is applied, okay? From T1 to T2, okay? The difference between T2 and T1 is delta T, okay? So P multiplied by dt, P is constant, so the integration of P is P multiplied by T, and then you put those terms, so it's going to be P multiplied by T2 minus T1, which is P delta T. Here, when we integrate mu double dot, u double dot is the second derivative of the displacement with respect to time. So integrating this with respect to time, it becomes the first derivative, okay? So mu dot, so it becomes m multiplied by the velocity. So here, this becomes the velocity, so this is the difference in the velocity, the two boundaries of the integration, T2 and T1. So m delta v, so delta v is the increase, is going to be the increase in the velocity due to that impulse. So delta v is simply equal P delta T, the impulse, okay, divided by the mass that it's applied on. So this is the velocity due to the impulse. So now if you have an impulse, the impulse results from a force applied over a time delta T. The velocity, you're giving a sudden velocity, increase in the velocity of that mass that is equal to that impulse P multiplied by delta T, the time over which it's applied, divided by the mass of the object. Okay? Now, after I remove this impulse, after I remove the force, what will happen? We have that object, it has this initial velocity, delta V, okay? This is the velocity it gained, okay? And then it will move freely, okay, under that initial velocity. If something is pulling it back, it will, start, moving fast, and then the velocity will decrease because something is pulling it back, okay? So after the removal of the force, the body will move freely as described before with an initial velocity. So the initial velocity due to this force is u dot naught, is b delta t divided by m. So after now, this is an impulse. Let's assume that that impulse is applied at some time tau, okay? Now, just due to this impulse, what's the displacement, or if we want to find the displacement at some time t, so assuming that we have an initial velocity here, the initial displacement is 0, the initial velocity is that one that we find here, u dot node due to that impulse b delta t divided by m, okay? How much is the displacement going to be after some time t? We solved that. If you have an initial velocity and in zero force, okay, zero displacement, u of t is going to be e minus e to the power negative zeta omega n t minus tau, the time from here to there, t minus tau, okay? U dot, sorry, u node cosine omega d t, which is t minus tau, so this cancels, this becomes 0 because u node is 0, okay? There is no initial displacement. But we have an initial velocity, so this is the initial velocity, b delta t divided by m omega t, okay? The mass, okay, is m omega t, okay? Why? Because omega n is square root k over, sorry, m omega d, that's b delta t divided by m, and then omega t was here. So u dot node divided by omega d sine omega d t minus tau. Why t minus tau? Because I'm assuming that we are starting the motion from here, so from here to the time t, it's t minus tau, okay? That's why I'm putting here t minus tau, t minus tau, t minus tau, okay? So the displacement at some time t due to an impulse at time tau, okay, is equal to this. But now, if I have a force like this, actually we have the structure moving under the effect of many impulses. I'm dividing the force here into a series of impulses. Can you see this? Each one of those is an impulse, okay? So how much is the displacement? This is the displacement due to an impulse of the force, okay? So if we have a force that is like this, all I have to do is to find the displacement at some time t. I have to integrate or sum the displacement due to all the impulses up to that point t, okay? So actually integrating, I'm integrating over here this formula that we found, okay? E power negative, so u at some time t is e power negative zeta omega n t minus tau. So I want to find u at some time t, so t minus tau. What's tau? Tau is, you know, the location where I'm integrating all these impulses. Each of those impulses is at time tau. So I'm integrating with respect to the impulses, so d tau over here. T is the time that I want to find the displacement. So I'm not integrating with respect to t, I'm integrating with respect to tau, okay? Tau is the changing parameter over here. I want to find at some time, at constant time t, okay? At certain time t, but I'm integrating all the impulses. Each impulse is at time tau, so I'm integrating with respect to d tau, okay? P of tau divided by m omega t sine omega d t minus tau dt. So this formula here is called the Duhamel integral, Duhamel's integral. So what's the Duhamel's integral? U, the displacement at some time t. I need to integrate e power negative zeta omega n t minus tau, okay? So t minus tau, I'm integrating with respect to tau, p of tau, okay? I'm integrating all the forces before that time t, okay? Certainly you're not integrating beyond t, so you're integrating tau from 0 to t. Okay, so you're integrating over here from 0 to t. Let's put the parameters over here, or the from 0 to that time t. Okay, so tau starts from 0 all the way to t. Okay, you don't integrate or use the forces, okay, after t. I hope you understand this part. What do I mean over here? Okay, to find the displacement here at that point. The displacement will be due to the force, all the forces applied on the structure up to that point. The forces applied after that time, okay, is not gonna give a displacement at that time, okay? What do I mean? I have an object. There is a force applied on that object, okay? There is this force is, you know, I'm giving you this force as function of time. I want to find the displacement at time 10 seconds. The displacement at time 10 seconds will be caused, will happen or will be caused because of the forces all the way from 0 to 10 seconds. The force applied at the 11th second, okay, is not going to have any effect on the displacement at 10 seconds. Okay, I hope you understand this, okay? Now this Duhamel integral, although it's a closed form like this, it's an integral form, but you can actually do this integration numerically. Okay, so how do you do an integration numerically? You have d tau. Okay, so d tau is the time step over here. So let's see an example over here. Let's say you have a force like this. So I give you the force. You have the sampling points over here. Okay, so you know p of 0, p of 1, p of 2, 3, 4, 5, 6, and so on. Okay, you know the forces. So simply, let's say you want to find the displacement at 20 seconds. How much is the displacement at 20 seconds? You need to integrate all the forces up to the 20 second. The force here ends at 15. So I'm going to do the integration of all those steps. So I'm going to integrate the integration. I'm going to calculate this integration, this for each step, and then the integration numerically becomes a summation. Okay? Exactly, you're trying to find the area under the curve drawn by this function. Okay? So here, P of tau. Some of you might ask here, let's see, delta t, we had a delta t here, there is no delta t over here, because delta t became the d tau, okay? So here you have 0 and 1, the first step here, okay? You're going to put P of this first step. T minus tau. Tau of this first step is 0. Tau of the second step is 2, okay, or 1, 2, 3. So tau is changing depending on the time step. T is constant. T is 20. I want to find the displacement at 20 milliseconds. This is milliseconds, okay? So here, you're going to do this calculation. Delta T is 1, okay? Or delta tau is 1, okay? So e power negative zeta. Zeta is constant. Omega n is constant. T is constant. Tau is the time of the step here, the location of the step. So here you have 0, and then this one becomes 1, 2, and so on, okay? So you're going to do, each time you're changing tau, okay, in this equation. And then you're going to do you're going to find this value without the integration. There is no integration. The integration is simply the summation of all of those, okay? And then d tau becomes delta t, okay? So simply, this d tau is equal to 1, so you calculate p of tau. Tau equals 0, tau equals 1, tau equals 2, and then you calculate p of tau, okay? This term here, p of tau, and then you multiply it by d tau, delta t over here, okay? You find this value, and then you find the integral. This value is the value here without the integration. You find everything here in the integration without integrating, okay? And then at the end, you sum the summation means it's the integration. So what does this mean? Simply, if you have, I guess you learned this earlier, if you have a function like this, okay? F of x, okay? This is f of x, and this is x. I want to find the area under that curve. So the area, this area, is the integration of f of x dx, right? So how do I, instead of doing the integration over here, I can do this numerically. I divide this into small parts, okay? So here, this area over here, you find f, okay? You find the height here, f1. Let's say this is f1, f of 2, okay? You find f of I, and then you multiply it by this width, which is delta x, okay? And then you sum all those slices, okay? So the integration of f of x dx becomes the summation of f of I delta x. So that's what we're doing over here. We have the Duhamel's integral, okay? It's an integration. Instead of doing the integration, I can simply say it's the summation of I e power negative zeta omega n t minus tau of I, the time at the step I, p of I divided by m omega d sine omega d t minus tau, and then multiplied by delta tau. So this is numerically. Okay? integration. Instead of doing an integration, we're doing a numerical integration. Okay? So as you see, knowing the forces at the sampling points, I can find the displacement or at some time step at 20. What if I want to find the displacement at 5? I need to, repeat this at 5, but the integral will be different, okay? You cannot use the same values that you used for the 20, because t here is going to be 5, okay? And you're going to integrate all the way up to 5 only, not to 20, okay? So that now, okay, let me put this in red, in black. So save. So this is an example over here, okay, of doing the numerical integration using Duhamel's integral. Okay, I'm gonna stop at this point, and then the next video we're gonna work on multi-degree of freedom structures, where all we mentioned so far, you had just 1 degree of freedom, a single degree of freedom. You had just the mass at one level. What if you had 2 levels like this, okay, where the mass is summed up at 2 levels, okay? How will we tackle this problem? This is what we're gonna discuss in the next video.